so we have done a lot of math so far. We have developed a lot of machinery, and gradually we will start doing more and more practical things with it. It doesn't mean you get rid of the math. The math will still stay there. We are going to start talking this week about chemical potential and variable composition systems. So the math will be there, but we will do more practical things with it. So today what we are going to do is to really use Gibbs free energy to think about how states of matter change with temperature and pressure. So for those of you who came late, I just made a point that I don't normally write down what are the topics we are going to cover every time. I do write it down in advance on the website every week, and you can see it over here. So this week we are covering properties of Gibbs free energy, including how variation in Gibbs energy leads to change in state of matter. And then we will move to variable composition system. Okay, so I'm going to ask you a very, very basic question that I'm sure all of us have experienced multiple times. And I want you to tell me why you think that happens. So this is a puzzle. We are not yet at skateboarding, ice skating. That will happen later. That puzzle we will visit later. But this puzzle right now is, why is it that as we increase temperature of a system at a constant pressure, why is it that at constant pressure, as temperature T increases, this, as in solid to liquid to gas, is the direction of spontaneous change? This is something we have a lot of experience, right? At low temperature, things tend to be solid. As we increase the temperature, they change to liquid. As we increase the temperature, they change to gas. Almost all the time, this is the behavior. There might be some freak things like superfluid helium and all, where you could have weird quantum properties. But this is the behavior that I hope all of us can agree upon, right? So the question is, why does this happen? Any ideas? Go ahead. Now you are a qualified, almost qualified P chemist. What is energy? What energy are you talking about? Internal energy, Gibbs energy, Helmholtz energy? Be rigorous. Which energy? Are you sure? What gives us the direction of spontaneous change at constant pressure? Which state function should we think about? Gibbs. Okay, so let's try to answer this. We need to think about G. Someone else was raising a hand. Someone else wants, Daniel, you want to say something? Okay, so we have to think about G, okay? It's not the internal energy. Internal energy on its own won't do it. What is the formula for G? H minus Ts, okay. So let's try to think about what happens at 0 Kelvin. At 0 Kelvin, what is G going to be? H, right? At 0 Kelvin, since T is equal to 0, G is equal to H. Okay, but that won't do everything for us. So intuitively, you can see, anyone else wants to take an intuitive stab at this problem as to why does it happen that at higher temperature we have, yeah, Andrew? Increase the entropy. So both of you had the right idea. You said something about internal energy. You said something about entropy. So it's really a competition between both of them, right? And this competition is set by temperature. So the intuitive idea for this is that at 0 temperature, only internal energy matters. At very high temperature, this term starts to dominate. Only entropy matters, right? So, but let's be more rigorous about it. So at 0 temp, so what we want to do is to make a plot which will capture G as a function of temperature for all three states of matter, for solid, for liquid, and for gas. We want to make a plot for G versus temperature for all of them. So in order to make this plot, let's start at the very beginning. At 0 temperature, where should be, let's say one of them is solid And let's say one of them is liquid, and let's say one of them is gas. So I have black, green, and blue. Which one should be solid? Which of these should have the lowest Gibbs free energy at 0 Kelvin, at 0 temperature? Go ahead. Huh? Lowest number. Which thing should have the lowest free energy? Whose free energy should be lower? Don't get confused in negative or solid. So let's say I have given you three numbers: -5 kilojoule, -10 kilojoule, and -15 kilojoule. Which one is going at 0 temperature? Which one of these is going to be solid? But we know if solid was on the top, we will have a problem. We know the thing with the lowest Gibbs energy is going to be the most stable. So at 0 temperature, we do know from common sense that solid is the most stable, right? So intuitively, we expect solid to be the lowest. But we can also make it more rational by thinking about this: G is equal to H. What is G? G is equal to H. What is H? Anyone remembers the formula for H? U plus PV, right? So if you just think about U now, what is U going to look like as a function of distance? We know for a given generic material, U as a function of distance looks something like this, right? Which of these is the most tightly packed, solid or liquid or gas? Solid. So solid, the atoms will be somewhere around here, very tightly packed, right? Solid. Liquid, the atoms will be somewhere around here, a bit more relaxed. And the gas, the atoms will have an even larger distance. Okay. So as per this, which one is going to have the highest internal energy on an average? Gas, right? Because you can see the solid has internal energy over here, liquid has internal energy over here, while gas has internal energy over here. So U gas, U solid, sorry, U gas, U liquid, and U solid. So if G was entirely U, if there was no contribution from pressure and volume, then we can see that U gas more than U liquid more than U solid. So the question now is about PV. We don't know how exactly PV will affect it, right? So what we are trying to do here, we are trying to figure out which one of these is the highest Gibbs free energy at 0 temperature. So if Gibbs free energy was only U, only internal energy, this should be gas on the top. But we don't quite know that yet because pressure and volume is, we don't know about that. So anyone has any ideas how to deal with that? Go ahead. Yeah, so what Corina is saying, if you assume ideal gas, for example, it just shouldn't matter, right? It's 0 temperature, PV is equal to nRT. That's the best we can kind of do here. If we assume anything more than ideal gas, it becomes confusing. But you can kind of get intuition for it that PV is equal to nRT. This is just assumption to get you some intuitive sense, right? If PV is equal to nRT, then this is all going to be 0 at 0 Kelvin. It just so happens that the internal energy term dominates respective to PV. The internal energy is so much more than PV that it dominates. So U is the term that dominates at 0 temperature. So gas is the highest, liquid is below that, and solid is even lower. And this basically conforms to our intuitive picture that at 0 Kelvin, everything becomes solid, right? You have one ground state, you know, it's going to have the most stable structure. So we have these curves. The question is, so this is the starting point of the G versus temperature curve. The question is, how will this curve change as a function of temperature? That's what we need to figure out. And in this lies the hint to your homework problem number 1 also. And the homework problem number 1 is something, I mean, I made it myself Saturday morning, so I don't think you can find it anywhere on the internet. If you do, that will be kind of crazy, except on my Twitter page, because I was so excited about making it that I tweeted about it. But there is no solution to it on my Twitter page. Okay, so let's make this plot. But young people, do they even use Twitter these days? I thought it's all like TikTok and Instagram. Huh? Twitter is the best? Oh, good. I was thinking about making a group TikTok page. Okay, so let's work with this plot. So far, what we have figured out is solid is, so this is temperature and this is Gibbs energy, okay? This is solid. And then we said at 0 temperature, liquid will have slightly higher Gibbs free energy, and gas will have even higher free energy. So the question is, so now we need to figure out how will these curves look as we increase the temperature. So in order to do that, we need, and this is at constant pressure, right? So we want to study the change in Gibbs energy with temperature at constant pressure. What is the partial derivative for this? Change in Gibbs energy with temperature at constant pressure. That's what we need to think about. How do we do this? In order to do this, we will look at the natural variables for Gibbs, which was G and T and P, right? And we derived a relation last time, which said, and you will be doing it again in the homework. So this homework has many easy problems also, where you just have to reproduce things from the classroom and you will get all those points. The idea being, it makes sure that you go through it. But dG is equal to VdP minus SDT. We showed it last time. So on this basis, what can we say about partial G by partial T at constant P? Go ahead. Negative S. So the change in Gibbs energy with temperature at constant P is minus entropy. So if we assume here that all these things, so what does it tell about the Gibbs energy of any of these? And this applies to all. This applies to solid, this applies to liquid, this applies to gas, ideal, non-ideal, anything. So what does it tell us about the Gibbs energy as we increase the temperature? Will it go up or down? Why? Who is talking? Oh, you're, yeah. Right, yeah, tell me. So why will it go down? Entropy is always positive, right? That was our third law of thermodynamics, that for which Corina got an ice cream. That S is equal to 0 at 0 Kelvin. And after that, S only increases, right? S cannot go negative. So entropy is, S is always negative. Sorry, S is always positive. I just destroyed the third law of thermodynamics. S is always positive. This means that partial G by partial T at constant P is always negative, right? So G as a function, G, the change in G with respect to temperature, it has to slope downwards. So let's say for solid, the curve is going to look something like this. It will have a slight, it will have a negative slope. It will keep decreasing as you increase the temperature. The question now is what happens to liquid? Liquid will also have a downward slope, right? It will keep decreasing as a function of temperature. But should the liquid curve decrease, it can do two things. It can decrease even slower than solid, or it can decrease very fast. Which one of these should be true? Go ahead, Daniel. Why?
Because it should have a lower energy than solid, higher temperature.
Think even simpler. Think in terms of entropy.
Oh.
Which one has the highest entropy? Gas has the highest entropy, right? So we know that S gas is more than S liquid is more than S solid. So if you use these things in equation number 1, if you use equation 2 in equation number 1, it tells us that partial G by partial T at constant P is most negative for gas. Gas entropy falls down as quickly as possible, followed by liquid, followed by solid. Okay, so in this curve, in this plot, the liquid will, let's draw all three now. This is solid. The liquid one is going to decrease at a faster pace relative to solid. It's going to look something like this. And the solid one will decrease even faster. Let's see if I can draw it right. It will decrease something like this. So let's take a moment to go back over what we did. And let's do a better job of drawing this curve. So things are not, everything is not intersecting in one point. So we are saying that liquid goes something like this and solid goes something like this. Okay. So there are three curves over here. Three curves with different slopes. And I love this plot a lot because it's just amazing how little bit of math comes and really tunes with intuition. If the nature of these 3 points at zero temperature was different, we would not have this behavior, right? So now let's think about, as we are increasing the temperature, which of these has the lowest Gibbs energy? So we start increasing our temperature from here. We start increasing our temperature, okay? We increase. Until this point, the black curve has the lowest free energy, right? So solid has the lowest free energy until this point, right? The green one and the blue one are above the solid. So by the way, what you're seeing here is your first introduction to something called phase diagrams. We will be spending some time over it, and making phase diagrams is all about drawing plots like this and seeing how they move with respect to each other. And it gets very messy as soon as you have 2 elements or 3 elements. You have to use something called Gibbs triangle. We won't be doing that. All the material sciences are your material science, right? That's why they're doing like, yeah, no, we won't do Gibbs triangle. It's a huge unfair advantage to the material scientists taking this class in phase diagram. They get so excited. We will be doing some phase diagram, a little bit of eutectic and all those things, but not too much. Okay, now at this temperature, the green curve is lower than the black curve, right? Blue is still highest. So as we increase our temperature from here to here, when the blue finally becomes lower, in this temperature, green one is the lowest free energy. And finally, at this temperature over here, you see that blue one now becomes even lower than green. So starting here, I'm drawing the colors just to give a sense. I mean, I could, of course, draw it here. It's all over the page, right? So what did I show here? So this temperature, what should we call it? This is the temperature at which solid changes to liquid. So we can call it T melting. And this is the temperature T boiling. So for 0 less than T melting, Gibbs free energy of solid is lower than others, right? Tm less than T boiling, G liquid Gibbs free energy is lower than others. T boiling less than T more than T boiling, G gas has free energy lower than others. And in order to do this, we use this equation that many of you have probably not seen before last class, dg is equal to vdp minus sdt, in order to show exactly how these curves will behave. So, so just to summarize what we did over here, we used 2 key ideas in this plot. The first idea was that at 0 Kelvin, G gas is more than G liquid, is more than G solid. In order to do this, we thought about the internal energy of the system and reasoned how will PV behave and came up with an intuitive sense. We could have been more rigorous, but that's okay for now. And then we said that G drops very slowly with temperature for solid, faster for liquid, and super fast for gas. That these are the two concepts that we used over here in order to derive something like this. So any questions about this? Those of you who, the 2023 of you who submitted the mid-course eval and said that the course is moving too fast, when I ask you for questions, please interrupt me and ask questions. If you don't ask me questions, of course, I will assume that it's all super clear, and I will just cover it and move on. So ask questions, and it's the best recipe to get participation points, and no one's judging. If you ask a question, sometimes simplest questions are the best questions. There was a professor here named Michael Fisher. You can go and Google his name. He very nearly won the Nobel Prize in Physics for something called the renormalization group in early 1980s. He used to teach this class 20, 30 years ago. Now he's very old, he's 90. And whenever Michael Fisher used to come to a seminar, he would ask the most obnoxious, but also simplest questions. And just, when I gave my job interview here, he was sitting in the front row. He was very old, so he fell asleep, right? So he fell asleep for like 45 minutes and then woke up and then asked basically something like, define simulation. Whoa, I don't know how to define a simulation, So any question is a good question, okay? So with that preamble, any questions? Go ahead. No. This curve, I just drew a linear model, right? It could be very complicated. Of course, there could be. And that's when you go to, it can be highly non-trivial. Right here, I just drew slopes, straight lines, but you could have curvatures. That boils down to how does entropy change? We have to look at the second derivative, right? And second derivative is complicated, especially in multi-component systems. These things can go up and down, and it becomes a huge mess. Any more questions? Okay. So in this equation, let's call it equation number 3, dg is equal to vdp minus sdt. We had one partial derivative which told us partial g by partial t at constant p is equal to minus s. We can extract one more partial derivative out of it, right? Let's write it on the next page. So we are talking about dg is equal to vdp minus sdt, equation number 3. And we talked about change in g with respect to change in t at constant p. Which other derivative can we talk about? Huh? Go ahead. At? And how much is that going to be? V. So let's do the same business here that we did last time and think about not how G changes with temperature or how different states of matter appear when you increase the temperature at constant pressure. But now think about the other way. You keep the temperature constant and you increase the pressure. And how do different states of matter appear? Okay. So let's call this equation 4. Let's use 4 to figure out how states of matter appear with change in pressure at constant temperature. By the way, are here any big Rick and Morty fans? A few? No one? Good. There is a new show called Inside Job. Have you seen it? On Netflix. It's just like Rick and Morty. It's like about Rick and Beth. You should watch it. I like it. I binge watched it all weekend. Very good. Professor's life is good. I got to make that conorium problem, which is so much fun, and then I binge watch TV. So I highly encourage becoming a professor. And then you get to do research. This is like the best job. And then teach, which is also a lot of fun. So let's think about the same curve now, similar curve, but now we are thinking about G as a function of pressure. So same question. At 0 pressure, let's draw 3 things. I'm going to use different colors. Which one should be solid? Which one should be liquid? Which one should be gas? Go ahead. You got it exactly wrong. Sorry. -5 participation points. Let's think about it. These things can be non-trivial. Let's work through it closely. You stay with me, Daniel. G is equal to H minus Ts. What is H? U plus PV minus Ts, right? And we are talking about zero pressure. So U minus Ts. So we can again draw that same curve. And there is a reason why you got it wrong. It's just confusing. You have to think carefully. So let's think of the same curve where U as a function of R and what we drew last time. And again, we have solid somewhere over here, liquid somewhere over here, gas somewhere over here. So as per this, once again, we see U gas more than U liquid, more than U solid. So as per this, gas should be highest. But then gas also has the highest entropy, right? And that's kind of bringing it down. So how do we account for that at zero pressure? How do we, Corina, does your argument work here? Last time you pulled out PV is equal to nRT, right? And you just said it's all similar. Can you help us here? Or anyone else? Go ahead, Hannah. Yeah, you're in the right direction, but basically it becomes a bit complicated. And once again, we use our bit of intuition in setting up this initial point. If just looking at U, it's going to be highest, and turns out that is the current trend. That is the correct trend. And think about as you decrease the pressure for something, gas tends to be the most stable phase of matter at very, very low pressure. Okay. As you increase the pressure, things tend to liquefy, right? You don't go from liquid to gas. So, but this really amounts to figuring out this term. If you just looked at U, then U gas more than U liquid, more than U solid, and it would do our job. And this would be gas, liquid, and solid. But we are doing a bit of hand waving argument for the second term about Ts. Because if we were thinking about S, then S is highest for gas than for liquid, than for solid, right? We used that argument last time. So basically what we are assuming here is that U dominates Ts. The contribution is coming from U at zero pressure. And I'm being hand wavy here in setting up this initial part. In getting the slopes, I'm being rigorous. In setting the initial part, I'm waving my hands a little bit, what is called like back of envelope calculation. So think about it. And if you don't like it, or if you have a better argument, send it to me on Slack and we can go back to it. But for now, let's just say that at zero pressure, gas, at zero pressure, gas has the highest free energy, followed by liquid, followed by solid. Is everyone happy with this? Go ahead.
So gas has a higher energy, so it's the least stable.
Yeah.
Right? But then, so like I'm literally thinking back to like Orgo Lab. When I turn the vacuum on, right, and I've got water on a treatment pump, whatever it pours. So it's obviously going from solid to gas. So at zero pressure, we expect gas to be which is like why
Yes, it is. It is confusing, but let's hold on for this. I think it's no clear way to answer this. In the first problem, we could use the ideal gas law and answer it. Here, there is no clear way, unfortunately. What we can answer is let's look at the slope first, and let's come back to it, okay? So I'm going to draw a big question mark here about these three initial points. And it's hard to answer. We cannot use PV is equal to nRT here. You will, like you tried, you had to use equation of state and work with it, but I don't know how to do it. So let's get back to this initial point in a moment. Let's first think about the slopes. And when you look at the slopes, you will realize that these initial points don't matter. They won't matter very much. So let's look at this equation 4. Let's go to the next page and draw this again. I'll give a moment so people can copy. So if U is much more than Ts at zero pressure, then gas, G gas more than G liquid more than G solid. But it might not be true. It depends on the material. So let's look at the slopes and then we'll see it does not really matter. So let's go to next page. So again, our equation is dG is equal to VdP minus SdT. And we said that partial G by partial P at constant temperature is equal to volume. So this means that irrespective of what is where, we do know what will happen to the Gibbs energy as we increase the pressure. Should it increase or decrease at constant temperature? What do you think? Yeah. Is volume positive or negative? If volume is positive, then partial G by partial P at constant T is positive. No, so okay, good point. I'm asking if pressure increase is positive. So you are right. If volume normally increases, then pressure decreases. But we are describing something here which is a bit different from that, right? We are saying, what if the pressure was increased at a constant temperature? What would be the corresponding change in delta G? So looking at this equation, since as you correct, what's your name? Joshua. As Joshua said, volume is positive, right? We don't know of something which has negative volume. That's kind of crazy. Even black hole has positive volume. You know? So if volume is positive, then if delta P is positive, delta G must be positive, right? So all curves must go up. Now, Joshua, stay with me and tell me which curve should go up the fastest, the solid curve, the liquid curve, or the gas curve? Which one has the highest volume typically, solid, liquid, or gas? Gas. So we gas, and it's not just slightly higher, it's like way more than liquid, right? We gas is way more than liquid, which also tends to be way more than solid, right? Maybe the second way more we can just change to more, but V gas is definitely much, much higher than liquid and solid. So this means that partial G by partial T at constant P for gas is going to be much more than partial G by partial T at constant P for liquid, which is going to be more than partial G by partial T at constant P for solid. Which means that the slope for the gas curve will dominate all the other curves. And that's why the initial point won't really matter. Do you have a question? Oh yeah, sorry. If they started, docking my pay every time I made a silly mistake, I would be so poor. I would be even poorer. Let's put it that way. So the liquid curve will dominate, right? If actually, let's make it, sorry, the gas curve will dominate. Let's make it even steeper. Let's make it look something like this. This is my gas curve. And the other two will look, the liquid will look something like this. And the solid will look something like this. The gas will dominate. And this initial point, I still don't know how it will look like. It's complicated, right? We have to think carefully. But it won't matter because anytime you increase the pressure slightly, zero pressure is a strange concept anyway, right? What exactly is zero pressure? Anytime you go to slight, the gas, the free energy of the gas with respect to pressure at constant temperature is such a large number, that G gas quickly becomes much more than G liquid much more than G solid. And that's the approximate picture of how Gibbs free energy changes with pressure. If you really wanted to get the right behavior between liquid and solid, you will need to worry about those initial points, which as we saw is hard, right? It's not a clear answer. But the one picture you can definitely form for it is the gas will never be stable. As you keep increasing the pressure, quickly enough, there will, even if the gas was stable at very low pressure, very quickly you will reach a pressure at which the gas becomes less stable. Is that clear? Any questions about this? No questions? Yeah, go ahead.
And dollar G is also equation. But then why is, and you don't know the value of dollar G, so how do you know the G is different?
So what we are saying here is delta G is proportional to volume times delta P, right? Approximately. That's what this equation tells us. Again, this is hint for homework for problem 1. Delta G is proportional to V times delta P. If you increase pressure by 1 unit, delta G will increase by a certain amount, and V is the proportionality constant. If you increase the pressure on a gas by 1 unit, the delta G of the gas will increase by crazy amounts. If you increase the pressure of a liquid by 1 unit, the delta G of the gas will increase by very small amounts relative to liquid, and for solid, it will be even smaller. You can make a table about this, okay? Let's make a table. Let's talk about delta P, let's say 1 bar, and let's say we have solid, liquid, gas, and let's say solid volume is, I don't know, 1 meter cube, liquid volume is 10 meter cube, and gas typically, if it's hydrogen, it will be enormous, it will be 10 to the power 4 meter cube. So delta G for solid will be approximately 1 unit, 1 bar multiplied by 1. Delta G liquid will be around 10 unit, 1 multiplied by 10, while delta G gas will be 10 to the power 4 unit. It just shoots up. That's the idea here. Any more questions? Yeah, go ahead.
For a liquid or a substance like water, which expands when it freezes, so the volume as a solid would be greater than that of the liquid, you just like flip the curve.
Yeah, but that expands as it freezes is only in a very tiny temperature range, right? We will visit, it's only 0 to 4 degrees Celsius, right? It's that weird range in which things happen. We will visit the phase diagram of water, and we will use this equation to look at the phase diagram of water and why it has some. Yes, you are absolutely correct. The nature of the curve changes and things go crazy for water. Yeah, we will. What's your name? Yeah, so we will visit water in great detail and see what happens with water, okay? Because that's how we will explain why ice skating is an issue. Water is peculiar. Water is very peculiar. I go to a conference every once in a while. It's called the Gordon Research Conference, and it happens on different subjects. The next one is on protein folding that I'm going to. I went to one on water. It's a 7-day long conference. It happens in the middle of nowhere in like New Hampshire or somewhere. It's the most aggressive conference. If you want to see scientists fight with each other, go to the conference on water. Everyone gets and bam, like not like punches, but you are wrong. You don't know anything. It's terrible. Water is so controversial. We will visit water and these curves, but for most materials, we can agree this is behavior, right? The fact that water expands on freezing, that's only 0 to 4. It's critical for life. If it did not happen, life would not exist, right? But we'll revisit that. So I'm gonna pause here, but I want to tell you what we are going to do next time. Next time, we are going to talk about 2 things. The first one will be quick. It's called Gibbs-Helmholtz equation. Go and read up on it, especially the second one, because the second one is where thermo gets really confusing. Okay, if you thought it was not confusing enough, it will get confusing. The first is Gibbs-Helmholtz equation. Here the idea is, so clearly delta G can tell us something about which state of matter is more stable, right? At constant temperature and pressure. We all hopefully agree that delta G is useful. But how do you measure delta G? In experiments, it's easy to measure delta H by doing calorimetry, by looking at the heat change during a reaction. If we could derive a relation between delta G and delta H, that would be very useful because we could do calorimetry to get our delta H. And from calorimetry, we could calculate what is delta G. And that's what Gibbs-Helmholtz equation does. The second one is this concept of fugacity. It's one of those concepts that us professors in the department often joke about. Do you understand what is fugacity? And depending on how many beers we have had, we say, not really, you know, it's confusing, but it's not that bad. You will all understand what fugacity means. And fugacity is something that takes the ideal behavior. It's related to pressure. It's hard to define what exactly it is, but we will get to terms with it. But basically it explains how Gibbs energy. So we will show next time that for an ideal gas, the Gibbs free energy varies as a function of pressure. Actually, something like this. We will draw this behavior. For an ideal gas, it looks like a log for ideal gas. For non-ideal gas, which is almost anything real, it does not look like a logarithmic plot. It looks something else. And fugacity is that thing, that concept, which allows us to use relations derived for ideal gas for non-ideal gases. So the reason why fugacity tends to be complicated is because really it is our first introduction to how to deal with non-ideal systems in a practical way. We will derive something for an ideal gas, and then we will show that we know very well that ideal behavior does not apply to anything in life, but how can such big relations still be useful? And fugacity will be our introduction to that topic. So I really recommend going and looking up fugacity a little bit, and we will start working on it. That's what we will do next time. And then in the Friday's class, we will start talking about variable composition system, which will lead us to another concept called chemical potential. So there are new concepts coming in the next 1 week. Come ready.